Welcome back to the course in Nuclear Medicine Physics. Today, we're looking at quality assurance of all the various devices that we've studied thus far in this course. We'll look specifically at dose calibrators, SPECT scanners, PET scanners, and also components of various CT systems as well. Anyways, enjoy.
Hi everyone, welcome to today's session, for which we've been really excited to have Dr. Barry Pointon be here with us. We've been anticipating this day for a while now. So I've known Barry for about 20 years when the two of us started taking this very course together, actually, by Dr. Anna Seller. And we also, both of us studied, did our PhD work and dissertations under supervision of Dr. Vesna Sasi at UBC. So just to tell you a little bit about Dr. Pointon, so Barry's been a physics instructor at the BC Institute of Technology, BCIT, for over 30 years, and mainly teaching physics and instrumentation for nuclear medicine technologists. And he's also an adjunct professor of physics at the Trinity Western University, and was recently appointed a Triumph affiliated scientist. He did his master's research as an experimental nuclear physicist at Triumph. And then later, as I mentioned, he did his PhD with Dr. Vesna Sasi. And recently, he's returned to fundamental physics research, joining the exciting international Super K and Hyper K neutrino experiments in Japan, with a focus on supernova neutrinos and machine learning data analysis. Barry is a very interesting character, and I've been intrigued by him for 20 years now. His other interests include interactions between science and religion, and I remember very fantastic discussions that the two of us have been having together on this. And he's studied theology at Regent College. Those of you at UBC have seen this physically at the UBC campus, probably. And he's also been appointed a fellow of the American Scientific Affiliation. I remember, this is a mutual interest of both of ours, and we've had very interesting discussions on this over the years, which continue. So without further ado, it's a real pleasure to have you here, Barry, and thank you very much.
Well, thank you for inviting me. This is it's a real pleasure to work with you again, and to be giving a lecture in this course, which we did together. And I have very fond memories of it. I have fond memories of Anna Seller and her work. So let's start off looking at, this is two parts. So the first part, we're going to be looking at quality assurance, and then we'll take a break, and then we're going to be looking at image reconstruction through some tutorials, computer tutorials that I've created. So if anybody has any problems with sound or that, let me know. I do have the chat here. I'm very grateful to be invited to give the talk. Now, just a couple of things. One, quality assurance. Now, quality assurance at first sight doesn't seem to be the most exciting part of nuclear medicine. And so, at first blush, it seems to be a lot of details. And quality assurance is actually probably would require a course to teach. So be aware that I'm going to be skipping on a lot of stuff, and I can't go through everything in any detail at all. And quality assurance is very much technology dependent. So depending on what equipment you're using, different quality assurance applies. So this is mainly going to be an overview of the ideas of quality assurance, with dipping in here and there to some specific examples of it. And so we're going to be looking at, first of all, sort of an overview of aspects of quality assurance, and then talk about a couple of, just briefly discuss some of the sometimes overlooked bits of instrumentation we use in a nuclear medicine lab. Then we'll look at quality control and assurance for SPECT, PET, And I'm not an expert in CT, but I want to introduce you to some concepts in CT quality control. Then we'll summarize. Then we'll take a break, and after the break, we'll look at the computer tutorial, and hopefully it will work. You know, software, when you want to show somebody software, it stops working. So let's start off with aspects of quality control. So I've taught nuclear medicine technologists at BCIT for over 30 years now, and I've had to think about ways of making quality control seem important. And over the years, I've developed this simple block diagram relating the different aspects of instrumentation and physics in the clinical setting. So actually, it's best to start off looking at the right. So the goal of medical imaging, clinical medical imaging, is to produce high quality diagnostic information. We want patients to get high quality diagnosis so that the doctors know how to treat or send them on for further diagnostic tests. But our ultimate goal is to produce high quality diagnostic information. So how is that affected by the physics and instrumentation aspects? And so if we move from right to left, the quality of the diagnostic information depends on the image quality, including the presence of artifacts, and also feeding into it is the way the data is analyzed and processed. We're not going to go into how we describe these things now, but we just want to see the chain of how they're related. Image quality and artifacts are affected by the camera performance, which is one of the major parts of quality control, and the acquisition protocol. So in this chain that leads to quality diagnostic information, we need to both assess and assure that we have high quality camera performance. And of course, the camera performance depends on the design of the camera, but it also depends on the functioning of the components and the functioning of the calibrations. So these aspects here of testing the camera performance to assess how well the camera is functioning, we may seem a long way from the patients as medical physics people, but we actually are a very important part of that chain. And so quality control is measuring and controlling the performance of the imaging devices and the supporting lab equipment. Now, as I say, we can't go through all of this, but I want to get across 4 basic aspects to keep in mind when thinking about quality control. One is that modern systems all require some sorts of calibrations to work properly. And so the first part of quality control is performing those hardware and software calibrations. We'll see what we mean by those as we go along. Once we have a calibrated system, then we need to measure the absolute performance characteristics to get a baseline of what the expectations are for the performance of the device. This is important in a number of places. One, if you're involved in designing new technologies or new designs, measuring absolute performance is a way of, that is nothing exciting or important. Measuring absolute performance is a way of assessing whether new technologies or designs improve on characteristics. Second aspect of measuring absolute performance is acceptance testing. So acceptance testing is the testing of new equipment brought into your department. You buy it from Save-On gamma cameras, and you bring your Save-On gamma camera into the department, and before you start using it, and if you've got very smart purchasing people, before you pay for the camera, you run a series of these absolute performance characteristics on it, and hopefully in the contract, you'll have numbers that have to be achieved before you pay for it. And so the acceptance testing gives the absolute performance measurements, and these are stringent tests that are done. While the camera is being used, number 3, we have relative performance testing. So this is routine testing of relative performance. We want to test on a certain baseline, a certain cadence, whether daily or weekly. whether the performance of the camera is changing over time. These are less stringent tests, but these are very important from a clinical perspective, because some of these tests, if the camera gives performance outside of what a good operating performance, then we actually say we can't use the camera that day. Another aspect of quality control I'm not going to go into is really for technologists, and that is best practices for patient scans. So keep these ideas in mind when thinking about quality control, and I'll come back to them again and again. There's a number of resources available for this. For acceptance testing, there's 2 handbooks produced by a subcommittee of the National Electrical Manufacturers Association. One of them is describing tests for SPECT cameras. The other is for PET cameras. These booklets don't give values that must be achieved, but standardized ways of testing. And so these are the NEMA handbooks. There's also guidance for acceptance testing in other articles. The IAEA has a number of publications. IAEA is the International Atomic Energy Agency. Please do not get it confused with IKEA. This is not a catalog of various types of bookcases or kitchen tables. It's IAEA, and there's a number of publications, and I'm going to refer to them. For acceptance testing, again, a number of professional organizations have papers or policies on these, and there's journal articles. Similarly, for routine testing, there's a number of publications which can guide us into how to do the measurements and so on. Especially important is clinically, there's accrediting bodies such as the provincial DAP. There's also suggestions from the equipment manufacturers. So just as a sample, if you are considering going into becoming a medical physicist, I would suggest you download these. These are free to download. So they're wonderful resources. And these are on the IAEA website. If you just look under publications, you can download these and many others. They include things like down here in the bottom right, quality assurance for SPECT systems. So it's a whole report on how to do quality assurance and gives a nice overview of SPECT. Then there's an atlas that is a set of images which describe quality assurance and types of image artifacts you run into for SPECT CT. You also have quality assurance for PET and PET CT, and another atlas, and then another atlas of quality control procedures. So I would strongly recommend, if you're thinking of going into medical physics, please download these and become familiar with them. And as I say, if you look at all these, the topic is huge, so we're not going to be able to go through all of them now. I want to start, though, with a very humble instrument, the dose calibrator. And what applies to this also applies to survey meters. I won't ask you, but some of you may have run into using a dose calibrator. It's a device which measures, when we put a vial in with a sample of radioactivity in, it will give a measure of what that activity in the sample is. So I hope you can see my little cursor here. So this cylindrical object is hollow inside. It's an ionization chamber. We have to tell it what radionuclide is we're using, and it will read out the activity. These are sometimes confusingly called a well counter. People like calling them well counters. That can be confusing in some respect because in other aspects of nuclear medicine, a well counter is a solid sodium iodide detector that's used for assaying and other things. So just be aware of which one is being used. So this is very important in PET for quantitative PET, where we do a well counter cross calibration. That is, we measure it. We use a measurement of the activity in a sample to calibrate a PET scanner for absolute activity concentration measurements and for evaluation of clinical SUVs. Clinical SUVs, we're not talking about sport utility vehicles. I hope that at some point you've run into the term standardized uptake values. This is sort of a semi-quantitative number that we use to assess whether lesions are likely malignant or benign. And I'll talk about that a little bit later. So if we're getting a measured physical value out, megabecks or millicuries or microcuries, we need to do quality control testing. So just a sample of the tests that are done. So every day, technologists put a set of standard long-lived samples in, and they test the readings to make sure that the reading changes with time. So they just want to make sure there's a constant reading. And so it doesn't matter what the setting is. So they may have one radionuclide in, and they may have the setting for another one. That doesn't matter. They're just checking whether it changes over time. If it does change overnight or from the day previously, if there's some long-term changes, then that's telling us there's something wrong with the equipment. Another test is called linearity. It's just testing the response over a range of activities, so that for high and low activities, we see that there's no systematic errors, and we also know the limits of what it can read. I'm not going to go through how these are measured. One of the tests I want to mention, though, is what's called an accuracy test. This is an absolute measurement of accuracy. So in the nuclear medicine department, there's a set of samples with known activity, long-lived radioactive samples that are NIST traceable. If you're not familiar with this concept, NIST is the National Institute for Standards and Technology in the States. They're the guardians, the keepers of the standard physical measures. So if you ever ask the question, what is a meter? What is a kilogram? The definitions of these go back to physical standards that are maintained by NIST. And so if we have known activities, that means the activities have been measured in a way that go back to the very basic physical standards maintained at NIST. And so these are routine tests that are done as part of quality control. Similar tests are done for survey meters. It's a similar device. I'm not going to go through the details. The reason I chose to spend a bit of time on this is a few years ago, an issue came up. And I remember going to a Society of Nuclear Medicine meeting, and this was a fairly important issue. It was published, I think this paper was by Dale Bailey in Australia. I'm not sure. But if you look at this horrifying title of this paper, it says accuracy of dose calibrators, blah, 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 unexpected findings. Unexpected finding. That sounds a little bit terrifying. So if you look at the abstract, I've highlighted the important words. They discovered systematic miscalibration of their dose calibrators, resulting in underestimation of quantitative accuracy assessed by SUVs. So they were having problems with their dose calibrators, and their quality control testing did not discover it. And I believe this was many years long, maybe even a decade. Armand might know more about the story. I don't know the story in all detail, but if you look at the results, it said 10 out of 14 PET systems underestimated the SUV by 15%, and an underestimated SUV could result in possible false negative tumor evaluation, which means we tell the patient they don't have cancer when they do. So the comment was that they were not able to do this because they did not have a good NIST traceable test source, because they didn't have a gallium-68 source where the activity was traceable back to the physical standards. So this may seem a little bit of overkill, making things NIST traceable. But this lack of a test source was not useful. So a question, how often do you perform tests? So some of the tests are performed daily. I think, I'm not sure how often the accuracy tests. I think the accuracy test can also be done daily. I don't remember how often they're doing it now in departments. So this should be picked up very quickly if there's a problem with the dose calibrator. But they were not able to get their accuracy.
So Barry, just to interrupt, yeah, I confirm we at the clinic we're doing that accuracy daily. We have those sources that Barry has been talking about, and every morning the technologists go and check and make sure that the activity corresponds to that activity that we're supposed to be measuring that day. So yeah.
So it would be, so when you're doing constancy, you're using these tests. If you do the constancy, you put in a source and you do the setting for that radionuclide, you're essentially doing the accuracy at the same time. So that's a bit of a horror story of failed quality control. Let's move on to SPECT cameras. So again, the quality control changes with the technology. This is more of a general overview of some of it. On the left, we have the old clunker of a gamma camera. We have it BCIT for training nuke med techs. On the right, we have a nice brand new image of a SPECT CT camera. Isn't it nice? I like the color. Is that a teal stripe? I think teal is a nice color on a gamma camera. Anyways, let's talk about the quality control. So I believe you've learned about SPECT cameras. SPECT cameras, the main parts are the detectors. The detectors consist of a collimator. Collimator is essentially the lens of the camera. If you take the collimator off, you don't get an image. And then you have a large area sodium iodide scintillation crystal. Then you have a set of 55 to 59 photomultiplier tubes. That's what you see here in the tin cans. Tin cans are actually new metal magnetic shielding. So each of these is a photomultiplier tube. It detects the scintillator light. These are connected to high voltage power supplies, preamps, and then the signals digitized in ADCs. The signals go into digital processing electronics, which by comparing the digitized signals from the PMTs, the location of where the gamma ray hit the scintillator is calculated. That location is called the address. Now, one of the problems with this design is that this design does not give uniform sampling of the light from the scintillator. PMTs, you see, are circular, and there's gaps between the PMTs. So if the scintillator light goes between the gaps in the PMTs, we don't detect it. And so that can cause some systematic errors in the addressing and some of the basic problems or some of the things that need to be addressed in a gamma camera. So, so underneath here is the collimator, here's the crystal, here's the PMTs. So again, going back, what do we do? First, we worry about calibrations. The first, one of the more important calibrations is called the uniformity correction system. It has three parts. First part is called the linearity correction, where the inaccurate addresses, which were caused by this non-uniform light sampling, are corrected. The non-uniform light sampling also causes the calculated energy of the gamma ray to actually be dependent on where the gamma ray hits. So if the gamma ray hits over the center of a PMT, the calculated energy is slightly too high. If it hits in the gap between the PMTs, it'll be too low. And so we need this energy correction so that the energy doesn't depend on energy. And that's especially important because we use energy windows, and that so it can actually affect the sensitivity and cause problems with the uniformity of the response. The third correction is what we call a flood correction, just sort of a cleanup. It is a correction that cleans up any non-uniformities. After the other two corrections, we routinely recalibrate it by doing a high count, 200 million count flood. So here's an example of what we're looking at. This is a nice paper from an IEEE symposium. So on the left is a gamma camera that is irradiated using what's called an orthogonal hole phantom. So think of getting a rectangular piece of lead the same size as the detector and then drilling holes at regular intervals. So every few millimeters that you drill a hole. And so what you should see is a pattern of radiation hitting the detector at uniform intervals. And what you should see is dots evenly spaced in every direction. On the left, you see a gamma camera detector without the linearity correction, without the corrected addresses. If you follow one line along here going down, this should be a straight line. Notice it's quite wavy. This is where the term linearity comes in. It's kind of not the best word, but it means if we irradiate a straight line pattern on the detector, it should look like a straight line on the image. But here, if we don't have the linearity correction, we get these non-linearities. And you can see a couple of gross issues with it. Notice the dots are closer together here. That would result in a higher count density in this region. This region corresponds to over the center of the PMTs. Notice here, between them, you've got them spaced out further. That would result in a lower count density. And so if I could ask everybody to squint a little bit, you would see that this produces a pattern where you see these areas, these circles of hotter and colder counts. That would be the uniformity image. We call that tubiness. I don't know if that's a real word or not, but tubiness. So this results in tubiness because we have these increased count densities correlated with the positions of the PMTs. Also at the edge, for reasons I'm not going to go into, you see that these are closer together. Again, if you squint, it would look like you've got a higher count density at the edge. We call that edge packing. So these are two intrinsic problems with SPECT camera detectors. And if these aren't corrected, these are big enough that if you tried to do SPECT on it where you reconstruct, you would have an image that would be unusable. The linearity correction essentially just recalculates where the address is. I'm not going to go into how. And this is what it looks like after the addressing with the linearity correction. So this calibration is very important. And if this calibration gets out of date in some way, if some of the parameters change, then this needs to be recalibrated. Otherwise, you run into these problems. So this has a big impact on spatial linearity and uniformity. Other calibrations include peaking of the camera, which means this is a procedure that technologist does, which means the energy window is centered around the appropriate photo peaks in the energy spectrum. This recalibrates the energy scale. The detector also requires tuning. That is, if you want to ensure that all the PMTs have the same gain. If one PMT begins to have more gain than the others, it will actually affect the uniformity. And so there's continuous systems that continuously tune the camera. And I'm sorry, I'm going to have to say this bad joke. It makes my students groan. You know the old saying, you can tune a gamma camera, but you can't tune a fish. Sorry, I apologize. Forgive me. Other calibrations are measuring the center of rotation, which is the relationship between the physical center of the orbiting SPECT camera and the center of the image. There has to be an alignment between the center of the orbit, which we call the axis of rotation, and where the center of the detector is. If there's a shift off, it will cause major artifacts in reconstructed images. It doesn't affect planar images, but it is a big problem for tomographic reconstruction. So center of rotation is measured routinely, sometimes monthly, sometimes weekly. In the old days, it had to be done more often, but cameras are more stable now. So now that the camera is calibrated with all these things, now we can measure the performance. The methods are listed in the NEMA handbook, which is available, but it's awfully expensive. It's like 50 pages long and it's $75 or something. I don't recommend you buying it unless, except for your department. Don't buy it for your own personal reading. And so this is what most acceptance testing is based on. And so the types of tests that are done are measuring resolution, which is the sharpness of the image, Linearity, as I said, is the accuracy of the addressing. It's shown by whether a line of radiation produces a line in the image. Uniformity is a uniform response, so that a uniform flood of radiation on the detector produces a uniform count density. MWSR, which is a bit of a mouthful, simply means the accuracy of addressing for different photon energies. So in SPECT, you sometimes use an old tracer called gallium-67, which has got 3 gamma ray energies that you have windows on. And if the addressing varies with the photon energy, it can make a mess of your image. Energy resolution is the blurriness of the photo peaks. Maximum count rate is related to detector dead time. So just give you a sense of the uniformity. So here's 4 images of rectangular field of view gamma cameras. The top 2, a uniform irradiation was performed. We see that the image looks roughly uniform. Maybe there's something at the edges here. So if you were doing an acceptance test, you bought a new camera, you want to see something like this, there are quantitative numbers associated with this. You can quantify the uniformity. This is what you don't want to see visually. These white spots, usually you see that here we have a higher count density than the surrounding areas. That could be caused by poor tuning. If we had tuned the camera and this was still there, that can be some deeper problem. If you just bought the camera and you see these little dots here, you would want to send it back. That means the crystal, which is supposed to be hermetically sealed, if the seal wasn't good and water vapor in the atmosphere leaked in, the interaction between water vapor and a salt crystal essentially can cause these little pock marks, and that's not acceptable. It's going to adversely affect the performance. Linearity is tested by a phantom where you have lead strips with 1 millimeter gaps between them, arranged so that the center of the gaps is 30 millimeters. You put this on the detector and you set up a flood field. The only gamma rays that actually hit the detector are the ones on these lines. And this is what you don't want to see. If the linearity correction has been calibrated, you still see this, something's wrong. It's probably that you made a mistake in the linearity calibration. So this waviness is what we mean by linearity. How wide these lines are what we mean by spatial resolution. And the way you actually measure the spatial resolution is if you take a profile through these line sources, or these lines on the image, you get what we call a line spread function, and you can measure the resolution by measuring how wide that is. Again, if we had more time, I'd go into the details of that measurement. So these are 2 of the measurements. Absolute performance, again, according to the NEMA protocol, they've got a section on measuring with the detector on. So the previous set was with the collimator on. If you just measure the properties of the detector by itself, they're called the intrinsic properties. If you measure them with the collimator on, they're called extrinsic or system values. And so we would measure resolution, we would measure sensitivity, which is sort of the global count rate per activity, and this will vary with the collimator. And one also can measure the maximum count rate with the collimator on with scatter. Won't go into why. Performance characteristics specific to SPECT include things like system alignment and the resolution when we reconstruct point sources. Again, this is analyzing how wide point sources look when they are being reconstructed. This is a very important measurement. It takes a lot of potential issues with calibrations. It can measure impact of that, and sensitivity. Whole body scanning has another type of system resolution. So this is done in acceptance testing. It's also done by the vendors when they are presenting you with the gamma camera. So this is a typical handout you get at a conference. This is a spec sheet for a gamma camera from Siemens. And you have to tell them that you're a physicist and interested to get these detailed ones. Otherwise, you get a glossy brochure showing a smiling technologist and a happy doctor and a happy patient. But what we want are the numbers. So if we go down here from the design and we look at the numbers, if we're interested in the performance of a SPECT camera, these are the numbers we're interested in. So you see here things like what is the intrinsic spatial resolution. So these are the numbers they measured at their factory. And what is the intrinsic flood field uniformity uncorrected with the flood correction? What is all these numbers? So they're all listed here. So these values were measured at the factory. And what you want to look for at the very end is to see that they measured it according to the SPECT standard ways of measuring. So they say values determined at the facility. If they came up with their own ways of measuring this, sort of like measuring pollution in a Volkswagen, if they came up with their own ways of measuring this, we wouldn't know how they measured it, and they wouldn't be comparable to other measurements. So the vendors measure them, these values, by the NEMA standards. So that was absolute measurements for acceptance testing. Again, routine testing, I was toying with the idea of going through this in detail, but covering this wide swath of QC, we can't go through them. Minimal testing that's done is SPECT cameras usually have a daily uniformity flood, and that is just setting up a flood field and measuring the uniformity, visually inspecting it, and also recording the specific quantitative values that are extracted from it. And let me just pull up one more thing for us. So I found in my files this setup of a quality control protocol. This was written many years ago in 2007 by Dr. Anna Seller when she was coming up with standardized ways for doing this testing. And so this is a nice protocol. I'm not sure whether they're still using this protocol clinically at BGH, but it includes things like, here's the different parameters for the daily testing. It says to check the daily uniformity, intrinsic or extrinsic, the frequency, what materials are used, how to do the acquisition for the different parts. So for the flood acquisition, it tells to acquire 5 to 15 million counts. It tells what energy window settings. It says what matrix size, but it includes a statement that this is manufacturer specific. So a nuclear medicine department should have these standardized ways of doing the protocols, either based on work by physicists involved with the department, sometimes just based on the vendor's recommendations. So this describes the testing. Just want to give you one result of the testing. I think this was probably 10 or 15 years ago at a camera at Children's Hospital. This was a dual head SPECT camera. If you look at detector 2 on the right, now that doesn't look so bad. If you look at detector 1, oh my goodness, what's that? So here this shows a big dark area of zero count density. This is indicative of a failure of a photomultiplier tube. If this testing wasn't done and the patients were scanned with this camera, the images would be very poor diagnostic quality. As a matter of fact, they could actually be could cause harmful diagnoses, incorrect diagnoses. Now, as I said, there's a number of recommendations for this. This is from the SPECT Quality Control Atlas. Sorry, let me here. So from the SPECT Quality Control Atlas, these are 4 different recommendations from the IAEA, from the American Association of Physicists in Medicine, from NEMA, and from the European Association of Nuclear Medicine. It lists their recommendations for tests to be done during acceptance testing daily. So down here, for example, we see most of the organizations recommend flood field uniformity and sensitivity to be tested daily. So question, let's see, so I'm just going to the chat. Are there many developments and technologies in nuclear medicine like SPECT? How much is the QC different? There are slowly evolving changes in the technology for SPECT. There's been a scattering of new technologies, like using solid-state CZT detectors rather than sodium iodide crystals and PMTs. That does have some effect on the specific QC, mainly that the results will be different, and they may have slightly different recommendations on how they're done. In PET, the technology is changing fairly rapidly, and some of the QC will be different. And I'll mention that a little bit when we get to PET. I don't have the details of how all the new technologies are changing. I know that solid-state detectors are in the new PET camera at BC Cancer, and that does affect some of the quality control. The NEMA protocols, for example, and the different organizations that give recommendations are trying to keep up by adding new tests as the technologies come online. So, for example, in PET, as PET time of flight technologies begin to be used, they've got testing of the time of flight characteristics, and I'll mention that. Yeah, that's a good question. And the technologies change. I can't keep up with them. And if you're working at a specific site, the important thing is to keep up with your particular technologies. So these are listed if you want to look in more detail in the IAEA publication. So going to PET scanners, this is a nice picture of a biograph. Notice the long bore here that the patient has to be in. So that's indicative of having a PET and a CT scanner side by side in the housing here, and one mutual bed. That's the PET CT camera. So again, we're going to go through some aspects of quality control, talk a bit about calibrations. Here's where the different technologies can vary. And again, the details vary with the equipment considerably. I can only go over some sort of generalizations. Armand could probably give you more details on the specific equipment that's being worked with and so on. So again, we'll look at calibrations, absolute performance, relative performance that we test routinely. So I believe you've gone through PET scanners. So PET scanner is a set of scintillation detectors surrounding a central aperture. A good PET event is when you have an annihilation in positron annihilation in the patient, resulting in 511 keV photons being given off in opposite directions, so that one detector detects one of them, another detector detects the other one within a very short period of time through coincidence detection based on some preset definition of what a reasonable coincidence timing window is. Because if we have multiple annihilations, we want to ensure that we're getting annihilations, so we're detecting 2 photons from the same annihilation. So this is an older camera, but I've got a nice cutaway of it. This is an old G Events. So in here is a block detector, which consists of one cut up block of scintillator cut into smaller sections, which have various names, like some people call them crystals, some people call them fingers or detector elements. We'll talk about these in a minute. This technology of one cut crystal, and you use 4 photomultiplier tubes to identify from the pattern of light which crystal was hit. So the calibrations involved depend on the technology. If the PET scanner does not use PMTs, this isn't relevant, but if it does use PMTs, the PMT gains and the energy windows have to be calibrated, sort of calibrating the energy scale, and the PMT gains have to be adjusted so that they're consistent throughout the camera. Otherwise, you're going to get some variations in the efficiency of detector pairs. In cameras that use this block crystal design, where you have 4 PMTs, but in this particular example, I think it's 64 cuts here. This is, again, the idea is each of these acts like its own independent detector, and the resolution in PET depends on how small you can make the detector. And so when a gamma ray hits one of these crystals, there's cuts such that the pattern of light going to the 4 PMTs will vary in such a way that you should be able to identify which of these 64 crystals the gamma ray hit in. So here's an example of what we call a crystal identification map. So if you flood the detector and you ask which crystal was hit, you see that they're not evenly spaced. So what you want to do is you have to set up areas where you say anywhere within this area in the identification map corresponds to a gamma ray hitting this crystal. So this is a calibration that is done for these type of block detectors. More modern block detectors have one of these elements coupled directly to a avalanche photodiode or a silicon photomultiplier. And so you don't have to do this addressing based on light distribution. And so it's easier. Again, Armand would be able to describe this in more detail. We also have to calibrate the coincidence timing. You have a whole lot of electronics between a detector and the coincidence testing. And so the coincidence timing for different detector pairs will have certain delay lags and so on for the signal being traced through the circuitry. And so you need to calibrate the system so that the coincidence timing is consistent for detector pairs. Another very important calibration also could be considered a routine procedure is normalization. This is a procedure which measures and comes up with correction factors for the relative efficiency of detector pairs. So again, if we go back here and we look at these detectors, so if a gamma ray hits here and here, what is the efficiency of this detector pair compared to all the other detector pairs? And so this needs to be measured to provide a uniform sensitivity within the detector ring. And so this procedure is called the normalization scan. Again, it can vary with the technology. I'm just giving a basic overview of it. And so what you want to do is measure very high count sinograms that you're going to be using to correct the clinical sinograms. And so here is a normalization sinogram. You see some sort of systematic variations. And just to remind you, a sinogram, each pixel in a sinogram corresponds to a detector pair, but it also corresponds to the angle and the radial position of a line of response. And so this is measured. And then, so you need to measure a correction factor for each pixel in the sinogram to come up with the correction factors. And then that is applied to your clinical, I just call this a projection sinogram here. So on a pixel by pixel basis, you come up with a correction factor that you apply for each of these, and that corrects any non-uniform response between the detector pairs. Now, if this is done brute force, it's very data intensive, and so there's some clever tricks needed to be able to collect the data efficiently. If you do this brute force, and you were doing this on the HRRT brain scanner, which I think has 4.5 billion potential lines of response, and you wanted 1,000 counts per lines of response, that means you would need 4.5 trillion counts. So brute force doesn't work. So there's all sorts of clever tricks that you don't need to do that. Here's an example of why it's important. This is a reconstructed image of one slice of a uniform cylinder. This is what it should look like. Just you see uniform count density. If you've got some significant variations in the efficiency of detector pairs, those variations somehow by the magic of reconstruction get transformed into circles in the reconstructed slice. So this is sort of if you see a lot of them, we sometimes call it a bullseye artifact. It's less obvious in clinical images. It's more obvious here. And this is why another type of quality control would be actually measuring the uniformity of a reconstructed slice. Even though NEMA doesn't have that as part of their protocol, it should be done. I've got to hurry up a little bit. Another calibration is measuring the relationship between slice voxel values of a reconstructed slice and activity concentration, so that you can recalibrate these voxel values into kilobecs per mil. This is done by putting a sample of known activity concentration, a cylinder with known activity concentration. You use the well counter dose calibrator to measure the activity. And this gives you a global calibration factor between the voxel values and the kilobecs per mil that you can apply. And you see that is necessary for the SUV, which requires the voxel values to be calibrated in activity concentration. So this is a very important thing for PET, and it's only useful if you've done attenuation, scatter, randoms, corrections, etc. So it's very important for PET SUV. So here's an example of PET SUV. Oops, I think this is the wrong PET SUV. So what happens when you Google PET SUV? You've got a PET in an SUV. Oh, well, here's a better example. This is just a graphic from GE. Don't worry about describing their version of SUV called QSUV. Here is a PET scan. Here we see a region of high activity, a lesion. We want to measure the SUV. The SUV is a number that the higher the number, the higher the difference between the activity concentration here and the expected average activity concentration in the body. There is a threshold that different groups use, above which you would consider the number saying that this is malignant, below which it is benign. And so if you have any thing that is reducing this number so it's below that threshold, that can result in false negatives. One pet peeve of mine is, as a physicist, I believe that all quantitatively measured numbers should have an uncertainty. And my what I would consider of greatest importance in quantitative PET is to get plus or minus numbers after these. If somebody gave me a physics lab with this number, I would take off marks badly because they didn't give the uncertainty. Absolute performance in PET, we're going to go through quickly. Again, here's a number of different things that are measured. Spatial resolution. Here we see something that is in the newer versions of the document where they talk about time of flight resolution. Here's an example of that question. How does quality control change with new technology? So this wasn't in older versions. It is in newer versions now. The time of flight is embedded in most new systems. Quality control, relative testing, routine testing of relative performance. Again, these vary with the vendors. GE has this daily quality assurance where they uniformly irradiate the detectors. So if we go back here and we take this ring and we cut it here and we unroll it so that it is flat, a flat rectangle, that's what we see here. So these are the different detector blocks and the individual detectors in here. And these are images based on the coincidence count rate, the singles count rate, the dead time. I'm not going to go into the details of that. Coincidence timing, energy. If there's anything that is particularly non-uniform or more commonly done, if this changes from one day to the next, it'll alert you that that something has gone wrong either in the components or the calibration. Another way of looking at quality control daily is by looking at sinograms acquired from a uniform source. So a sinogram in PET, a diagonal line in a sinogram is all the coincidences between one particular detector and the other detectors, or detector blocks, if we want to look at it in the bigger scale. So if we should see these as having fairly uniform count density, again, this is cleaned up by the normalization scan. But if we see an area where we have very low count density in a diagonal line, that's a clue that there's a problem with a particular detector block. So here's an example. So this is a clinical sinogram, but if we see a diagonal line like this, that's a problem with the detector block, and that's going to cause problems in the reconstructed image. Again, these are done with different frequencies. And so some of these are done for acceptance testing, some are done daily. These are the recommendations in this publication from IAEA. Again, I don't have time to go through these, but just be aware. So for example, coincidence timing is done daily. The accuracy of PET-CT registration is on acceptance. Just very quickly, CT components. So modern SPECT CT and PET-CT have either a full CT scanner or have CT components of an X-ray tube and CT detectors hanging off them. Again, they have these aspects. Again, I'm not going to go over them in detail. We can break them into two parts, though, the QC of the scanner and the QC of the combined system. Calibrations that are important for the scanner itself. These, I'm putting them in the category of calibrations. They may not fit there, but that is measuring of the CT number. That is the relative value of the attenuation coefficient in the object you've scanned. CT number, if you haven't done CT, this is a value relative to water. So the CT number of water should be 0 by definition. And so you want to test that you're getting an accurate CT number out. A value that's very important for measuring dose, patient dose in a scan, is measuring the CT dose index, which is, I'll describe in a minute. I'm going to put some of these performance characteristics for CT together. Daily, there's different tests that are done involving warming up the tube, doing an air cal, which is a blank scan with nothing in the scanner, and looking at the sinograms or reconstructing it to see if there's any detector-to-detector variations, any non-uniformities, similar to what I showed with sonograms and PET. Again, this varies with scanners, so don't count on this covering all scanners. Then there's the scanning of a simple water-filled cylinder. It's not radioactive, it's just water-filled cylinder. The reconstructed image is assessed for uniformity to see whether or not that CT number is what it should be. It should be close to 0. And assessment of the noise. And then there's other routine tests that are done monthly or quarterly. I'm not going to go into them. and then annual tests. These more stringent tests usually involve a very complicated CT phantom, which has various components. It's got sections where you would measure uniformity. It's got line pair phantoms, which are line pair parts of the phantom, which are used for assessing resolution. And I want to mention the CT dose index. This is a way of measuring the amount of dose that is deposited in an acrylic cylinder for a certain set of CT exposure settings. So we control the KVP and the MA and the rotation speed and things like the pitch. And we want to measure regularly for different CT settings what the exposure is. And so we do these measurements and come up with something called a CT dose index. There's actually various versions of that. And then for the settings, we can come up with another number for a certain scan of a certain length through the patient. We come up with the dose length product. So these numbers appear when we do a CT scan, and they're based on these measurements. And so we can assess what the patient dose is. For the combined system, main thing is we want to get system alignment so that when we use the CT for attenuation correction, that the attenuation image or the attenuation map aligns with the reconstructed emission image. And so we have various phantoms that have got parts that are detected by CT and parts that are detected by PET or SPECT. And so this type of alignment needs to be done. So again, I just give you these for your interest. So in this publication, here's different procedures that need to be done for the CT scanner. And these are how often they're done. And it's nice, it says who it's done by. So maybe this will be used sometime in the future. The medical physicist doing these. And these are done by the technologist daily. And again, we don't have time to go through them. So I do feel better, though, giving you the resources to look this up if we don't have time to go through them. And again, keep in mind that these vary between systems and they vary over time, all the testing. So I hope you got a good understanding of this. But again, the purpose of this is in the end that we get the highest quality diagnostic information for our patients. And that information is absolutely amazing nowadays. So I started off doing PET with the Brain Research Center back in 1989 with Tom Ruth's group. And we were debating whether PET would ever become clinical. And we all agreed back then that it couldn't become clinical. And of course, anytime you hear some scientists say something's impossible, they're proven wrong. Okay, so any questions? We'll take a quick break and I'll set up the next part. Any other questions? Anything to add, Carlos? Armand, anything to add to that?
Maybe I'll just add a little anecdote, but because sometimes people think, as you were saying, we're doing this QC and we do these measurements every day. Why do we have to do this every day if every day these measurements look like they're working? And sometimes people say, why do I have to do this? We already know that it's working fine. But as an example, hopefully it works fine. That's what we want to see. But as an example, we keep track of this every day. Something that happened recently in our clinic is one day our dose calibrators started shifting. We saw it shifting, and then we did the measurement the next day, and it was shifting a little bit more than the day before. So I immediately noticed, okay, this is a trend. It's showing us that this equipment is actually starting to fail. So then you go and you talk to management in the clinic and you say, hey, we need to buy a new dose calibrator. And they say, why? And I'm like, well, because it's failing. And how do you know it's failing? So then you come and you show this data, and he's like, look, we know this trend, and look, now what's happening is coming, and we're not gonna be able to use it in 2 weeks if we continue at this rate. So there's all this data that's proving this, and of course, then you immediately get the budget to buy the new dose calibrator. A similar situation happened in a hospital that I know in a province in Nova Scotia on the east coast of Canada. It was for another type of equipment, but then they had to go and ask for a lot more money than a dose calibrator. Of course, the ministry came back and like, why are you asking for this? And all the physicists had all this data of all this QA. They were able to completely justify why is that we needed the money. And then they were able to replace the equipment. So, I mean, this is to show that these things work, that it's important to do them, that I know maybe sometimes it's annoying, why do we have to do this every day? Every day is passing, but the moment that it doesn't, it's important to know your equipment because you track it on time, and it's important to have it to be able to justify these purchases when they happen. So, yeah, I don't know, just wanted to show, yeah, these things matter.
Yes, great, fantastic. Thank you very much.